Hello, and thank you for tuning in. I'm Dallin from the BYU racing team, and for my fluids lab 4 assignment, I wanted to do something new and look more into how turbulence models affect wall calculations and vice versa, and then also verify these CFD simulations against wind tunnel data. Just a bit context in Formula of Society of Automotive Engineers competition. We have used different airfoils throughout the years. We started with like NACA 6412s just because those are easy to understand the characteristics. Then we transferred over to the Selig 123 or S1223, which has a higher Reynolds number or higher lift for lower Reynolds number flow or slower non-dimensionalized flow compared to its viscosity. And then now I'm toying with the idea of moving to the Epler 423, which is another high downforce, low Reynolds number airfoil. Now, if we look back at the NACA, we can see that our peak coefficient of lift at around 15 degrees at a faster speed is around 1.6. But if we move to a higher downforce airfoil, like this 1223, we can see that we are now like 2.3 or 2.4 on our coefficient of lift at our maximum. Now, however, though, the stall characteristics are very abrupt on this airfoil. It is a very sensitive airfoil. So, although the Epler 423 doesn't have nearly as high coefficient of lift, it taps out at about 2 on this X-foil data, the stall characteristics are much more gentle and forgiving as it's not nearly as sensitive. So, to verify that my CFD is matches what's in the real world, I went to find some wind tunnel data. This is from Michael Selig, a paper by him and one of his compatriots. And we can see here on this paper their setup for their wind tunnel. Now, this is um, a little bit complicated so that they could adjust the angles of attack and get all their sensor readings. And there are some components that would have affected the flow that they didn't put into this picture. And so instead of trying to model all of this perfectly and figure out how I could replicate their exact experiment, what I did is I just created a 2D simulation, which is essentially just a cut down this cross section, and then from there solved it and extrapolated out all the data that we needed. So the wind tunnel data that they provided is here on this chart. We have the angle of attack versus the coefficient of lift for a Reynolds number of 2e to the fifth, or 200,000. And I also found wind tunnel data for the Epler 423, which is also a Reynolds number of 200,000. And these also roughly match the X-foil data that we saw before. Now, one thing I will say is all of these sources that I'm using, I'll link down in the description so you can look at them there. But moving back to our simulations now, we can now compare and see how well our results matched up with the wind tunnel data. So this is a plot of our residuals of the simulation. Although these residuals could be better, I found that they were converged enough for our needs, just because they were leveling out and coming down. But especially our coefficient plots, that plots our coefficient of lift and our coefficient of drag have plateaued out and they aren't changing much at this point. So even if we could get lower residuals, our coefficient of lift is only going to change by maybe a thousandth, a couple thousandths. And so in the grand scheme of things, we're plotting and comparing our values, and the fact that the papers only had a confidence of 15% in how close they were to their results, or an error percentage of 15, I was happy with this simulation. One thing to note and to view here is that we have our velocity scene, and so you can see at the top of the airfoil, the air is moving faster. On the bottom of the airfoil, it's slowing down. And what that causes on the airfoil in general here is that we can see that we have a low pressure region from the air moving fast on top and a high pressure region on the bottom from the air slowing down. What this means is that like, this high pressure region will want to fill the low pressure region in a sense, and so we have a net force pushing up on this airfoil, creating lift. Now, to properly model this airfoil and the flow going around it, a CFD software will split this area up into a ton of cells, and we'll set the inlet up in the front and the outlet where the air comes out the back. And we refined all of these little cells behind the airfoil, especially to capture results of the wake. But then another important refinement, even more important, I would gander and say, is that we have the prism layers modeled. Now, these inflation or prism layers capture the velocity profile of the boundary layer. And we have extremely small cells here at the wall of the airfoil in question. And the airfoil lost like 2 millimeters out of the meter long that it was to be able to let these prism layers naturally wrap around. If it comes to a point, the mesher will really struggle with that, and we won't get the wall-away plus values that we want. Now, what is a wall-away plus value? If you want a 20-minute explanation, this video by Fluid Mechanics 101 is brilliant and does a great job going through what wall-away plus is, how boundary layers form, and how CFD codes deal with all of this. But the short answer is wall-away plus is the height of the wall here, or height of the cell at the wall, the very first cell. And what it does is it models the viscous sublayer. Because as we look at this velocity profile at a wall, right, you will increase speed as you get closer to the free stream value, and as we get closer to the wall, it'll decrease. A more turbulent flow would come higher, would have more momentum at the wall, and then come up. But essentially, we need enough resolution at the wall to properly model the viscous sublayer. That happens if the wall y plus value is less than 1, and if it's not, then we'll get this buffer layer flow, and that can really mess with the CFD solver. And by the way, this is if you don't want to watch a 20-minute video and you'd much rather read a 5-minute article from Wikipedia, there's also this article as well that goes over the bare essentials of how it works, but not so much the fluid understanding of it. But if you just need a wall y plus value parameters to get your prism layer started, Fluid Mechanics 101 made a great calculator. You put in the speed, the length, or your chord, the dynamic viscosity you're using, and the density. You tell it about the wall y plus value you're aiming for and the number of layers, and it'll give you these values that you can plug into your CFD. And so we can verify that the CFD worked properly, or the prism layers worked properly on the mesh. As we plot it and see that our maximum wall y plus is less than 1, you should check this value partially into your software, or partially into your simulation, if not at the very end. If you do it at the beginning, it will not be correct, as the flow hasn't been properly solved for yet. And you can see how, on this plot, how we have the turbulence layer changes, or the boundary layer changes over the chord of the airfoil. At the beginning, it's the dark blue signifies a laminar flow. This green color signifies a turbulent flow. So we can see that the boundary layer eventually starts to break off and becomes turbulent, especially after this peak spot on the upper suction side. And because of the boundary layer separation bubble here, the CFD code is increasing extra turbulence at this area, and that's why we have a value above 1. Further research should be done on how to solve this and overcome this, but for the scope of all the time that I did spend, I was unable to eliminate that extra turbulence. But then, so going to the actual design manager now, right, it iterated through all the angles of attack and found the coefficient of lift and plotted it. And we can see in this linear region of about -2 degrees all the way up to maybe even 15 to some extent, right? The CFD code is relatively accurate in figuring out what the flow should be. But as we get to a higher angle of attack where stall occurs, the CFD code just jumps up and down and it doesn't know how to solve. So I thought maybe our assumption that it's a steady flow is incorrect. So I moved to an unsteady solver, and we can see that we still have, it's a different issue, but now we're under predicting the coefficient of lift at low angles of attack, and then we're over predicting at higher angles of attack, and we're not really properly modeling things. If we go to a velocity scene for one of these points at the high angles of attack, we can see that there's this separation of the boundary layer at the stall, which is what we predict, and that's what. But the fact that the CFD code can't properly model it, even with an unsteady simulation, means that something else is going wrong. And we can see here at the coefficient plots, right, that we're not leveling out anymore. And in fact, the drag is higher than the lift. And so something clearly is going on that is not correct. And here's a plot of the Epler 423 data that is steady. And we can see, though, that just before, as we described, the stall characteristics aren't nearly as sensitive on this airfoil, that it performed better, and we are still correct in this linear region, even with the steady assumption. So what could be causing us to be so wrong, though? It's probably the fact that I chose to use a 2D simulation. So on this website, it goes through how the incompressible Navier Stokes equations, which we use a Reynolds average Navier Stokes equation, which is beyond the scope of this little lab. But essentially, what we derive and what we come to understand when we do 2D, we have an infinite direction in the z out of the plane. And so our vortex stretching term, which is this, ends up being 0. That lack of a vortex shedding term is the reason why, right, this vortex coming off the back of our airfoil here, it should be dissipating with time. Now the free stream flow is smoothing it out and forcing it to kind of follow back. But the effects that the vortex has are being overestimated by the fact that we're using a 2D simulation. So if we were to model a 3D setup and try to capture all the effects that were present when the coefficient of lift and drag calculations were done in the wind tunnel, that would most likely have a better result. If we are just caring about a quick, simple way to set up like a multi-airfoil configuration, as long as we don't have a large amount of separation, we can accept those results and move forward in our planning. And so I'm very grateful for this opportunity to get farther into an understanding of how CFD codes work, how the fluids impact how CFD codes were designed, and I thank you for tuning in. I hope that this was a useful portion of your time and that your faculties have been expanded. Thank you, and I hope you have a wonderful day.